Okay guys, we're going to go over chapter 2, section 3, which is uncertainty in data. In your book or ebook, you're on page 47. If you're using your workbook, you're on page 22. You may want to go ahead and pause me and do your kind of pre-read if you're in your workbook. But something that I want you to kind of think about is after we take our data, how do we use it? How do we analyze if it's good data? How do we know how to calculate with those values that we've recorded? So we're going to go through this section together. If you have any questions, always feel free to ask. I have jumped too far. So go ahead and label up your notes if you're taking it on paper. And we're going to get started. Now, the main idea of this section is that measurements contain uncertainties that affect how a calculated result is presented. So our goal anytime we're using data is to make sure that it adequately represents the relationship we're trying to prove or that we have found, okay? So what do you know? What do you want to find out? What have you learned? Go ahead and fill that in as always. Hopefully you do come back and do the what I learned. You know, I ask you that if you're in class with me, and I try to ask you that if you're doing it online. So here we go. I think I clicked it. There we go. Here we go. Main questions for today. How do accuracy and precision compare? What does one mean versus the other? How can the accuracy of data be described using error and percent error? And what are the rules for significant figures? And how can they be used to express uncertainty in measured and calculated values? So you're going to see me use sig figs every time we do any calculation. And I'll explain why we do that here in a few minutes. Review vocabulary is experiment. An experiment is a set of controlled observations that test a hypothesis. A set of controlled observations that test a hypothesis. Here's all your new vocab. So if you want to take a minute and go ahead and jot down all those vocab words and write the definitions from the text, please feel free. I'm moving ahead. Accuracy refers to how close a measured value is to an accepted value. So, did not mean to do that. An accepted value is the right answer. So accuracy is how close am I to what I should be getting. So if you look at the picture down here, this is accurate. Accurate is dead on. I'm supposed to be hitting the bullseye, and I do. Precision, on the other hand, refers to how close a series of measurements are to one another. So that would be like a cluster here in our archery analogy. So you can be precise, but you have to have multiple trials. You can be accurate with one trial. You can be accurate with all of your trials, or you can just have numbers everywhere. So you can be pretty much everything. You can be accurate and precise. You can be accurate but not precise. So say your other shots were somewhere like this. That's not really precision. You can be precise but not accurate, or you could be neither. The data can run all over the place here. So I'm going to move ahead. Start clicking, sorry. When we talk about accuracy, we have to talk about the error in our values to know if the value is actually accurate. So here is our second definition. And error is defined as the difference between an experimental value and an accepted value. So say I'm supposed to be getting 100 on my test. That would be accurate. But instead I get an 89. So my error there is a subtraction. I have missed it by 11. So what we do is we take the value of the accepted, and we basically subtract we take our measured and we subtract the accurate value. So let me show you what that looks like. experimental minus accepted. So that's how we find this error value. So here, 1.54 minus 1.59 is negative 0.05. I was below the value, negative, by 0.05. In the next case here, I got 1.60. Well, that minus 1.59 means that I was above the accepted value by 0.01. So you can see how we can find our error each and every time. Now, let's look at this data at another light. Look at the density that they came up with. Look at student B. Okay, look at student C, which is already boxed in. Which of these are most precise? So here it tells me that this last one is most precise because our error is about the same. The error is about the same. But the most accurate, we take that average value for them. The most accurate was actually this first one. So it was more accurate, but it was less precise. And this one on the right was more precise, but less accurate. Okay. Experimental minus accepted, that's defined as your error. Now, we saw on the last page that error can be positive or can be negative. It tells me if I shot above or if I was below. But percent error, I don't care if I'm above or below. I just want to see how far off the mark I am. So we take the absolute value of the error and we put it over the number we were supposed to get. So how far off were we from the accepted value? And then anytime it's a percentage, you multiply by 100. Anytime. Be sure you have this equation down. And if you're not moving as fast as I am, both of these equations are on page 48. So you can just let me keep talking if you want. We'll go do some practice problems. Practice problem 1. Technically, example problem 5 in the chapter. Student A's density data in table 1, which I've got it in front of me, so I'll give it to you again. Use that data to calculate percent error in each trial. Report your answers to 2 places after the decimal point. Okay, so let's look at student A. Trial 1, student A got 1.54 grams per centimeter cubed. Trial 2, 1.60. I don't know why I did that, sorry. 1.60 grams per centimeter cubed. And trial 3 was 1.57. And remember, the accepted value for this density was 1.59. Now, I'm going to stop. Sorry, you may not be able to see that. The accepted value, 1.59. I'm going to stop writing the units here because they're going to cancel anyway. So we're going to find the percent error. So I know my error already, but I'm going to show you how to do it the long way. Trial 1. So I need the absolute value of my experimental minus my accepted, because that's on the top. So it's going to be 1.54 minus 1.59. And I'm going to put that over the accepted value times 100. So you're going to find your calculator and you're going to type in 1.54 minus 1.59. I get negative 0.05 like we saw before. Get that closer for you. So I don't need the negative, so I'm just going to type in 0.05 because I want the absolute value. And I'm going to divide it by 1.59. Click enter, type in times 100 or do it all at the same time. I don't care. And then you're going to get 3.1. 2 places after the decimal point, 3.14%. Okay, 3.14%. Trial 2. Experimental was 1.60 minus 1.59 divided by 1.59 times 100. Same process each and every time. I don't have to worry about that negative because it is a positive value. Divide it by 1.59. That's an ugly number. I don't like it. And then I am going to multiply by 100. That's even a very small number, 6 3 by the time I round it, 0.63% error. That's good. Okay, let's look at trial 3. On this one, I'm going to do 1.57 minus 1.59, and I can already tell this is going to be a little less stellar than the last one because my error was larger. Same process, error, experimental minus accepted, over accepted times 100, but this is for trial 3. So same process. I don't want the negative here because that will be a negative on top, so I'm just going to type in that difference again. Divided by the accepted times 100. Hopefully you can see all of that work. So in this one, my percent error was 1.26%. Okay. Of these trials, my best trial was trial 2 because it had the lowest percent error. If you get up into the high percent errors, you're going to find that your data isn't very reliable. So you don't want that. All right, so here is where we're going to move on. I want to point out that right here and in math, your entire life, they have told you where to round. In science, we don't do that, okay? In science, our rounding is determined by the measurements that we are taking. So it's determined by how good is my ruler, how good is my graduated cylinder, how good is my triple beam balance or my electronic balance. So let's go talk about that. All right, normally we are limited by the tools that we have available. Now, this is the biggie. Please write this down. Significant figures include all known digits, everything you can see with your eyeball, and one estimated digit, okay? Everything I can read based on the tool in front of me, which here we have a ruler, everything I can read, and I go out one more place value with an estimate, okay? So look at this picture here. I can see the 5. I can tell it's 5.2. I don't know what the last bit is because there's no lines there to tell me for sure, so this is going to be my estimate. I know 5. I know 5.2. This spot right here is my estimated digit. And everybody's might be different. This one says 0.03, but you could have read 0.01. That's why it's estimated. So here, we're going to go with my measurement on this ruler is 5.23 centimeters. Always use a unit, okay? I always say in class, we don't like naked numbers. If it was a measurement, it should have a unit, okay? That was those base units we were talking about. They're very important because it tells me what I'm looking at. I know centimeters tells me length, okay? And keep in mind, a centimeter is 1/100th of a meter. So 1 centimeter is 1/100th of a meter. Or if I flip this, 1 meter equals 100 centimeters. All right, based on kangaroos hopping down mountains drinking chocolate milk. All right, let's clear this. Let's go watch this in action. Oh, I lost the video. Okay, so you do the same thing on a thermometer. You do the same thing in a graduated cylinder. You look at the numbers you can read, and you always go out one more place value. So on a thermometer, on your basic thermometer, you are going to see the actual degrees in Celsius. In my class, you'll use Celsius. So say I read that the outside temperature right now is 78 degrees Celsius, or Fahrenheit. We convert that to Celsius, because I told you all to change your phones. And let's say it says 26 degrees Celsius. So if it's 26 degrees Celsius that I can see with my eyes, because there's lines at 20 and then I see a line at 26, I'm going to estimate that 10th place. So I would say 26.2 maybe, depending on where the actual line is for the alcohol in the thermometer. Okay, let's go over these rules. I rewrote these rules. This is not what your textbook says, so please write down my rules. They're much better, I believe. All right, so for significant figures, Page 51 has the rules in your textbook, but I've changed these up, so you're welcome to use them, but mine are better. Rule 1, non-zero numbers are always significant. So it's any number 1 to 9. They are significant. They count. Rule 2, zeros between non-zero numbers are significant. So that could be 101. That could be 3.0042. Those are significant. They count. So do these. Okay, sandwich zeros count. I'm going to skip to rule 4 real quick. Leading zeros. So if I say this big old number, these leading zeros never, ever, 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 ever count. And you'll hear me say this multiple times. The zeros up front strictly are holding the places of these place values that there is no measurement in, okay? So leading zeros again, never, ever, 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 ever count, okay? The ones that cause most trouble are these trailing zeros. So that's like if I said 140,000. These are trailing zeros, right? Or if I said 1.2300. These are trailing zeros. They only count if there is a decimal in the number. In this value, 140,000, do you see a decimal point? No, no decimal point, so these zeros are placeholders. In this value, do you see a decimal point? Yes, therefore these do count. Let me explain why, and these real numbers do count. They count because I could have stopped this number, 1.23, right there. But if there are values there, that means that whatever device I'm using gave me this, and this is my estimate. So those are significant. Okay, over here, this means that this is my known value. This means that this could be my estimate, or this could be my estimate. In this case, since there's no zero there, I'm going to go with this as my estimate, so this doesn't count. Okay? So, if I say something like a counting number, or if I give you a conversion that's known to be fact, those have an infinite number of significant figures because it's a definition. So if I said 1 dozen equals 12 donuts, those are counting values. I know it's 1 dozen. So that's technically 1.000000 on into infinity. Equals 12 equals 12.0000 on into infinity. So anytime we're using whole numbers like this that are definitions or counting values, they have an infinite number of sig figs because nothing's really measuring them. I'm looking with my eyes. Okay, now that you're thoroughly confused, let's go do some practice. We're going to always start looking at these based on the rules you hopefully have already written down, and we're going to figure out how many sig figs are here. So I look at this value and I see zeros up front. Those are called leading zeros. They never, ever, 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 ever count. And then I hit this 4. Well, yeah, it's a real number. It's going to count. This is a 0 sandwiched by 2 numbers, so it's going to count. This 2 is going to count, and 3 is going to count. The last one I'm worried about is a trailing 0. If it's trailing, I look for a decimal. The decimal is present, it counts. Okay? So here I found 1, 2, 3, 4, 5 sig figs. Or you'll sometimes see me write 5 sig figs. SF means sig figs. Let's go look at the next value. We're going to start at the left. I got a 4, that counts. I got a 0 sandwiched, it counts. And I got a 5, it counts. Then I have a bunch of trailing zeros. Do I have a decimal in the number? Nope. So they do not count. The decimal is absent, so they do not count. Okay, so that's 3 sig figs there. All right, on these, you're going to go practice with 35 through 37, okay? 35 through 37. I do want to show you that if we were to do these in scientific notation, how that would change. So let's go look at this guy in scientific notation. If I were to change this, 1, 2, 3, 4, oops. See, I brought that 0. That's why it's significant, because you bring everything else. But those ones up front went away. Oops, forgot my times 10 to the. So here it's been changed 1, 2, 3, 4 times 10 to the negative 4 grams. And notice 2, 3, 4, 5. I still have 5 sig figs. Let's go look at this one. 1, 2, 3, 4, 5. Ooh. So it's 4.05, but since those zeros don't count, since they were simply placeholders, I don't have to bring them. Okay? So here, again, 3 sig figs. And that's how you always tell if they were significant or not. I dropped these guys, but I kept this guy because it was still there when I was done moving my decimal. Over here, that was the whole point, was to get rid of those zeros. So that's why they're not significant. All right, moving ahead. Let's talk about rounding. You've been rounding for a very long time, so I don't want to make it too difficult for you. So keep in mind, when we start rounding here in a minute, because you're going to calculate and you are limited to a certain number of digits based on whatever you're doing. So here's the big takeaway. Answers should not have more significant figures than the original data with the fewer figures, and they should be rounded. So I'm going to show you. If I were to do this problem, notice that's a real long answer when I only multiplied it by 44. So that tells me that number's way too big and you don't want to write every digit and you're going, where do I round? Well, I'm going to tell you here in a minute. But keep in mind, if you're rounding, if it's less than 5, leave it alone. 4 or less, let it rest. If it's greater than 5, round up. So 5 or more, raise the score. 5 or more, get one more, something like that. And then if it's, don't stress over these last 2 rules. I hate that. Just stick with the first 2 and you'll be fine. If you go on to AP, we will have more of a discussion over that, but right now you're good. Okay. 2 different rules. You ready? If you're adding or subtracting values, like say I needed to find that volume displacement earlier. So I put irregularly, I'm going to try that again. I put an irregularly shaped object into a graduated cylinder because I can't do length times width times height. It's just not going to happen. And I need to figure out how much water it displaces so I can tell its volume. When I do that, let's say I start at 10.0, that's my estimate, 10.0 milliliters. And then when I drop my little marble in, it raises to, let's say 15.2. My estimate is 0.2, 15.2 milliliters. So what's my actual volume here? Well, you're going to say, what was the change? It was 15.2 minus 10.0. Perfect. So what we're going to do, because you technically should be using the same cylinder, so it should be all right, but you're always limited to the original measurement with the fewest decimal places. So make sure that you write addition and subtraction. Round the answer to the number of decimal places as the original measurement with the fewest. So here in this case, 15.2 minus 10.0, well, they both have 1 decimal place, one number after the decimal. So there I'm good. So I'm going to say 2, I'm going to say 5, and I'm done. My actual answer there is 5.2. The next part is if they don't match. So let's say that for some reason I said 15.486 and I need to add, the next one is like say 4.3. Let's look at these values. Which of these is least precise? Which of these is the worst tool I've got? Well, it's the one that gave me the least number of decimal points. So this is my worst measurement. So I'm limited to the number of decimal places in that worst measurement. So here, yeah, I'm going to pull these numbers down. But when I round, I'm stuck rounding to the tenths place. So what's this going to round to? 19.8. And let's just pretend it was centimeters. Okay. I am limited to the number with the fewest decimal places. Okay, because when we add or subtract, we stack those decimals. Now, this is the one we use most of the year. If I were to be doing volumes, if I were to be finding density, what am I going to do? I'm going to round the answer to the same number of significant figures as the original measurement with the fewest significant figures. So let's say I'm finding volume. One side is 1.2 centimeters. The next one is 3.42 centimeters. And the last one is 9.8 centimeters. Well, which of these has the fewest digits? Well, this guy has 2 sig figs, this guy has 3, and this guy has 2. So I'm going to round to the fewest. I'm going to round to 2. I'm going to do my calculation. That's what I get for making up numbers. And here's the number the calculator gives me. That's too many digits. I am limited to using 2. So, actually, I'm pretty proud of myself for this. If I'm going to use 2 significant figures, I'm going to use these 2 digits. I look behind to determine my rounding. It's 40. But I can't just write 40 because that means this 0 doesn't count, so there's only one significant figure. What do we do to fix that? All you have to do is put a decimal. By putting that decimal where it belongs, that makes the 0 count. And if you ever get stuck and you're like, I don't have the right number of sig figs, this number's too big or too little, put it in scientific notation and then you get to determine which ones to use. So here this would be 40 centimeters cubed. Okay, same with division. You go by the number with the fewest significant figures. So counting becomes really difficult. Now, we're going to go do a practice thing and we're going to practice rounding. Okay, so 38 and 39, you go practice your rounding and then we're going to do some calculations. Calculate the volume. Oh, look. Calculate the volume of a book with the following dimensions: length, width, and height. Well, we're going to multiply those 3 values. So let's take a look. This has 1, 2, 3. 3. Oh, they're all the same. So I'm going to report to 3 significant figures when I'm done. Okay? Because I'm only doing one type of operation. So I'm stuck with 3. I'm going to take it. I'm going to calculate. That's a big old number. It comes out to 2293.149. I'm only allowed 3 digits. And you're like, which ones do I pick? Start with the highest place value. So here, I need the 2, and this 9 is going to stay a 9. What do I do with the next? I just put a 0 in. If I don't put a decimal, that 0 doesn't count, and I still only have 3 zeros. And this would be centimeters cubed. That's not one of those derived units, so I had to multiply the 3, and my units are now centimeters cubed. Okay, so the practice problems. Remember, addition and subtraction, line up your decimals and go by the fewest decimal places. Multiplication and division, you need to go by the fewest significant figures. And even if I were to look at this with scientific notation, it's only the front numbers that matter. So like if I were to change this and I'm going to do a calculation with this value, this is only 3, okay? Do not look behind it. None of that has anything to do with your significant figures, okay? Go ahead and do 40 and 41. For addition and subtraction, and then do 42 and 43 for multiplication and division. And if you want to, do 44. That might be good for you. Okay. Oh, well, here's the addition. I think I messed up these two. Yeah, I definitely did. They were in the wrong order. Sorry about that. But it's okay. Let's practice adding and subtracting. A student measured the length of his lab partner's shoes. If the lengths are blah, 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 what's the total length? Well, hopefully you know total means I got to add them. So I'm going to line up my decimals. I mean, you're probably just going to pick up a calculator, but I want to show you. It's easy to forget what to do if you don't show your work, which in chemistry, you always show your work. If you haven't noticed, there's a sign over there that says no work, no work, no credit. Okay, so I'm going to add. Now let me clarify this for you, because I really like to crowd my stuff over here. If I got rid of all my units, these are still all centimeters, so when I add, they're still going to be centimeters. But if you notice, there's no value here or here. That means I'm limited to rounding to the 10th place again. That's the last place I have a number, so that's the last value I can trust. So put my 0 or my 8 here. 8, 9, 10, 11, carrier 1. 6 and 6 is 12, carrier 1, bring your decimal. 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Yep, carrier 1, 2, 4, 6, 7. My value here is 77.218, but that's not okay because I really can only trust it to this 10th place. So look behind, I'm going to round it to 77.2. That's how you accurately, based on data, based on measurements, that's how you accurately round. So every time your math class tells you just to round to a certain place, they're just letting you be lazy, okay? These are the rules you should be using to round values. All right, get off my soapbox here. All right, essential questions. You know you got to answer these, plus the other questions that I've added throughout. How do accuracy and precision compare? How can the accuracy of data be described using error and percent error? What was the point of that? And what are the rules for significant figures, and how can they be used to express uncertainty in measured and calculated values? Remember, it had to do with how good the tool I'm using is. If you have any questions, please email me. I know this gets confusing. There are lots of YouTube videos out there. And bye.